modeling. Okay. Got it. Okay, so I need to get it in two places. Good? Yes, okay. Okay, so the goal is to explain this particular method of modeling binary systems that are sources of gravitational waves. The particular method is this self-force theory, which focuses on modeling binaries where one body is much bigger than the other one. So this is a rough outline. I'm breaking each of these 2-hour blocks into roughly 2 lectures. And the first one, as I mentioned, is going to be really about gravitational wave astronomy, just to put everything in context, why we're studying this and what is the ultimate goal here. So I'm going to describe the overall picture of the two-body problem as a method of modeling gravitational wave sources, and then get into this specific method, gravitational self-force theory. Then I'll have two much more mathematical lectures. There's almost no math in the first lecture. Much more mathematical second and third lecture, and then some results from the model. And feel free to interrupt me at any point. Okay, so big picture, gravitational waves. Probably everyone has some notion of this already. The idea is we have two compact, massive bodies, almost always black holes, sometimes neutron stars, in a tight orbit, circling around each other, spiraling inward until they eventually merge. And as they spiral around each other, they generate these gravitational waves that come out and are detected by our detectors. So this is a picture of one of the detectors. This is one of the LIGO detectors. And the topic of interest here is modeling these sources and the waveforms that come out of them, because we can't detect the signals, and we certainly can't extract any interesting science out of them unless we have a model that tells us how a waveform relates to the source that created it. So this is an observational science that depends entirely on theory. You can't do the observations without the theory. So another thing I'm sure everyone has seen, this was the first detection in 2015. This was the first gravitational wave ever detected. So here you see the data, which is quite noisy and scribbly, detected by LIGO. In black, you see the theoretical prediction for the underlying physical waveform. It was produced by a pair of black holes orbiting around each other, merging, and then you have left with one black hole that vibrates down to a Kerr black hole. And you see the prediction matches pretty well with the data. So that was just the first. Of course, that was a major breakthrough, Nobel Prize winning. Now we see these things all the time. Here I'm just showing you the waveforms from the first 2 observing runs. So even by the end of the second observing run in 2018, we already had seen a lot of signals. So this was no longer about just a breakthrough of detecting a gravitational wave. Now we can start to do astrophysics. We can start to do more observational science from all these signals to get a better picture of, the population of black holes and their history out there in the real universe. So this is just the first 2 observing runs. By the end of the third observing run, we'd seen about 90 signals we were confident in. And now the 4th observing run is underway, and I'm told we're detecting new signals once every few days. So this is now a part of everyday astronomy, observing black hole mergers and sometimes neutron star mergers using gravitational wave detectors. Now, for these kinds of signals that we currently observe with ground-based detectors, they all have a very similar, well, not all, most of them have a very similar morphology. They all look kind of similar. So what you see is basically just a sinusoid where the frequency is increasing with time, the amplitude is increasing with time as the two bodies get closer and closer, until we have this merger, this peak, and then you're left with just a single body that rings down to a stationary state. Now, I said that we need theory in order to do any of this science. For this kind of signal, there's a very clear breakup into different kinds of models. So in the Earlian spiral, when the two bodies are far apart, we can use post-Newtonian theory, a weak field approximation to full GR. Then, as they get closer and closer and eventually merge, really the only very accurate first principles model is numerical relativity, where you're solving the fully nonlinear Einstein equations on supercomputers. Then the very last stage, where you just have a single object that's ringing down to a stationary state, that's well described. If it's a black hole, it's well described by black hole perturbation theory. We have a Kerr metric plus little perturbations that dissipate away with time. But those kinds of signals are really just what we're currently seeing. In the future, we're going to see a lot more, a lot of different kinds of signals from different kinds of sources. So over the next 2 decades, we expect to have a much larger array of gravitational wave detectors. This is what we currently have. We have 2 LIGO detectors in America. We have Virgo in Europe, and we have CAGRA in Japan. CAGRA is operational, but isn't yet at sufficiently high sensitivity to actually detect anything, but it is observing along with LIGO and Virgo. LIGO India always seems to have an insanely ambitious timeline. They say they're going to be up and running in the next few years. I don't know how realistic that is, but the idea is that they're just taking LIGO technology, LIGO instruments, and just moving it to India. And the reason for having more detectors around the Earth is we get better sky localization to see where the signals are coming from. All of these are quite similar. In the future, we're not going to just have detectors on Earth, we're going to have detectors out in space. So the big one that is funded and moving forward is LISA, which is a European project with NASA as a secondary partner. And so this is going to be a totally different kind of detector, still the same fundamental principle of how we detect these things, but it's out in space, so it doesn't have noise from the Earth around it, so it can detect totally different kinds of things. Each of these arms is going to be millions of kilometers long, so it's quite a large detector. In addition, we're going to have much more sensitive detectors on Earth, what are called 3rd generation ground detectors. So those are things like the Einstein telescope, which is planned for Europe, and Cosmic Explorer, which is planned for America. We expect these to be built on a roughly similar timeline as LISA, 10 to 15 years from now. LISA, has a planned launch date. It's scheduled. These ground-based detectors are not yet funded and scheduled, but the expectation is that they will be built over the next 15 years or so. There's also been proposals for another space-based detector called DeSiGo by Japan. That is also not funded, so I'm not sure if that's going to happen, but people are still pushing for it. And 2 more space-based detectors, both planned in China, and both basically modeled on LISA. So once we have this much bigger array of detectors, we're going to see much more. So first off, we're going to see a lot more signals, but more importantly, a much wider variety of signals, different kinds of systems. So if you have any interest in what kind of things we're going to see, I highly recommend you go to this website called gwplotter.com, where it has sensitivity curves of all the different planned detectors and current detectors, along with what kinds of signals they can detect. So here, this black curve, this top black curve, is the LIGO detector. That's the sensitivity band of LIGO. What we're seeing here is basically the amplitude of a gravitational wave plotted versus frequency. So the higher on the y-axis, the more visible it is to us, the more we can detect it. And then down here is just the frequency of the waveform. So anything that's above the black curve is something we can detect. This red band here is the first detection, the one I showed you a couple slides ago, which was two black holes of roughly 30 solar masses each. In general, the kinds of signals we detect currently are very similar signals to that. That's what's shown in this kind of pink band here. Then this lower down black curve is the Einstein telescope, so it's seeing roughly the same frequency range, meaning roughly the same kinds of physical signals, but just much improved sensitivity, so we can extract much more science from the signals. And then the space-based detectors are over here on the left. Because they're not being contaminated by noise from around them in the Earth, they can see much lower frequencies. I shouldn't really say see. They can hear or detect much lower frequencies. And because they can see much lower frequencies, they can see much bigger objects. So roughly, the frequency of a gravitational wave, you can estimate just from kind of a Keplerian frequency. You just put two bodies on a circular orbit and you use just Kepler's law for the frequency. So Kepler's law is this: the frequency is square root of the total mass divided by the orbital separation of the two bodies cubed. Hopefully you've learned that back in second year of undergrad or something. And for tightly bound binaries, the orbital separation, the capital R there, is comparable to the total mass. We're not interested in really weak field systems, we're interested in strong field physics. So the orbital separation is comparable to the total mass. So you get that the frequency is roughly 1 over the total mass of the system. So as you detect lower and lower frequencies, you're detecting larger and larger masses. And what LISA is particularly designed to see is systems containing massive black holes at the centers of galaxies. So I'll discuss them more in a bit. All the things we see over here in ground-based detectors are, a few solar masses, a few tens of solar masses, a little bit into the hundreds of solar masses. Down here, we're going to see millions of solar masses. So I'll get into the particular kinds of things we can see. Yes, of course. Yep.
The orange on the left-hand side.
Yeah.
The orange background. It is background. Yes.
So the detection of this stochastic gravitational wave background was actually just announced a few weeks ago. So it's lots of different sources, lots of different potential sources. The main one is supermassive black holes, so 10 to the 9 solar mass black holes orbiting each other.
Okay, because I wasn't sure if it would be like a background from supermassive stars or based on this universe.
I think both. I think we can't distinguish them at the moment.
And ETA is what experiment?
This is the International Pulsar Timing Array, which is made up of a bunch of different pulsar timing arrays around the world.
So this is the sum of all.
Yeah.
Okay.
Yeah. So yeah, pulsar timing arrays are basically having gravitational wave detectors, the size of the galaxy. Okay, so we're going to see lots of different kinds of signals. And again, I'll explain more about the different types in a second. But the key point I want to drill in is that different kinds of signals require different kinds of models. So as I showed you a few slides ago, the current signals we detect generally all look very similar to each other. So those are quasi-circular, so almost exactly circular, comparable mass binaries. So two objects that are roughly the same size as each other on an almost exactly circular orbit. It's only non-circular in the sense that it's dissipating energy in gravitational wave emission, which is causing the circle to shrink with time. And for those, we use post-Newtonian theory combined with numerical relativity, as I mentioned. So these are kind of the two most important axes in the binary parameter space. The orbital separation, how far apart are the two objects from each other, and the mass ratio, how big is one relative to the other. And so the signals we currently see are over here, where the two objects are roughly the same size. In the distant past, they were very weak field. They gradually, it's quite hard to tame this red dot here. They gradually get closer and closer through gravitational wave emission until they get into the regime of numerical relativity, where post-Newtonian theory is not sufficiently accurate. But then down in this corner, we have a totally different framework for modeling binaries, which is based on perturbation theory, specifically what we call self-force theory. So this is where one body is much larger than the other body. And I'll say in a minute why numerical relativity and post-Newtonian theory are not accurate in that regime. So why is this regime down in the corner of interest? Well, as I said, with future detectors, we're going to see a lot of different kinds of binaries. But also, even with current detectors, just with LIGO and Virgo, we're already starting to see a wider range of mass ratios. So we have seen a signal where the mass ratio is 1 to 26. 1 to 26 is not crazy. The 1 over 26 is not that small a number. But as far as numerical relativity is concerned, that's extreme. That's very difficult to model. So as far as NR is concerned, we're already pushing to the right here in what we can observe today. So let's get into these different kinds of binaries. So the main one we see is these comparable mass binaries. That's what we see today. That's what's observed by what's called the LVK network, which is LIGO, Virgo, Cagra. Now, LISA will detect these same kinds of binaries, comparable masses, tightly bound orbit, but just much bigger masses. So rather than seeing two objects that are both 30 solar masses each, we're now going to see two objects that are both 30 million solar masses each. And from that, you can extract a lot of physics because the signal is just so loud. The SNR is a million times larger. Now, we'll also see just the earlier stages of the current binaries we see. Because in the distant past, those binaries that we currently see had much lower frequencies when the bodies were much more widely separated. And so we'll not only see much heavier binaries with LISA, we'll also see the earlier part of the current binaries we see. So then you can do multi-detector detections, where LISA sees the early part of the inspiral, and then it tells LIGO, okay, in 1 year's time or something, you're now going to see that same binary when the two objects are about to merge. So through these different kinds of detections, we'll learn about fundamental physics. We'll learn about, is GR the correct theory? We'll also learn more about the population and history of black holes over the whole cosmic history of the universe. And as I mentioned, with these kinds of binaries, comparable mass binaries, the early stages are well modeled by post-Newtonian theory, weak field approximation, and the late stages are modeled by numerical relativity. What I didn't mention is that you don't actually use numerical relativity waveforms when you're doing your data analysis, because a numerical relativity waveform takes at least about a week to generate, more like a few months if it's a very complicated system. And for data analysis, we actually need waveforms that are generated in about a millisecond. So orders of magnitude faster. So the way we actually build current present-day models for data analysis is through things like effective one-body theory. So effective one-body theory is just a framework for describing all kinds of binaries, and it can just take inputs from anything. So it takes inputs from post-Newtonian theory. It's originally kind of inspired by and based on post-Newtonian theory. It takes inputs from PN. It takes calibration input from numerical relativity. It takes input from self-force. It takes input from everything to build kind of a universal model to describe the waveforms. There's also other kinds of things like surrogate models. So surrogate models just take a lot of numerical relativity waveforms and basically just construct a complicated fit of that data. And the other main way of generating complete models that go from early in spiral through merger through ring down is called phenomenological models. And those are really, they just look at the shape of the waveform and come up with super simple analytical approximations that work remarkably well. So things like they look at the amplitude as a function of time, and they say, well, it looks a lot like an arctan. They just put in a sum of arctans, and it's magic. It works really well. GR, it turns out, is not as complicated as we think. Okay, so you'll have some model that incorporates information from NR and from PN and gives you a fast waveform model. And this is very well developed for current signals. So just to show you what kinds of systems we're looking at here, because I'm going to compare and contrast that with the kinds of signals we're going to see soon. So this is already a somewhat significant. It's going through Zoom, so it's actually not working correctly. Okay, imagine a beautiful, smooth motion. Beautiful waveforms coming out. And yeah, they just spiral in quasi-circularly and merge. Now I'm going to contrast that with totally different looking waveforms from totally different systems. And those systems are extreme mass ratio inspirals, or EMRIs. So here we've got one body that's much smaller than the other one. And this picture is a bit of an exaggeration because it's really much, 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 much smaller. So these are systems that occur in galactic cores, where you have a massive black hole that's maybe 1 million solar masses, like the one at the center of our galaxy, Sagittarius A star. And then a stellar mass object, maybe 10 solar masses, is orbiting around that massive black hole and eventually falling into it. Now, what's interesting with these signals is that the evolution is very slow compared to the orbital period because it's proportional to the mass ratio. So the rate of change of the system is proportional to little m over big M, the mass ratio. So because of that, the number of cycles or the number of orbits we get in the strong field regime before the little object plunges into the big one, the number of cycles scales with the inverse. So the big mass over the small mass. So we get roughly 10 to the 5 orbits in the very strong field regime before the stellar object plunges into the black hole. And these are going to be important signals for LISA. So LISA has 2 really important types of signals. It's got other ones as well, but the 2 really big important ones are massive black hole binaries, the ones I mentioned before, where you just have 2 massive black holes orbiting and then merging. And then these guys, EMRIs. And these are systems that on that binary parameter space I showed you, these are systems that are way off to the right, really, really extreme. Because of that, we use this tailored method called black hole perturbation theory and cell force theory. So I think it's worth thinking about the actual environment in which these systems form. So I said these are massive black holes in the galactic cores, so the centers of galaxies. And these days we actually, well, first off, we can actually see some of these black holes with the Event Horizon Telescope. But also over the past few decades, just with the ordinary astronomy, we've looked at stars orbiting around black holes, particularly at the center of our galaxy. Now, again, this is not going to work so well because it's going through Zoom. But this is a time-lapse movie. Oh, actually, this one's significantly smoother than the last one. So pay attention to this white dot here. as it comes down and then zips back up. So that is a star, just an ordinary star orbiting around something that we can't see. And the something is the black hole at the center of our galaxy. So even though I've been working on these systems called MRIs, I've now been working on them for almost 20 years, I only saw this movie fairly recently. And I found it really fascinating that we can already look at stuff at the center of the galaxy, and we can already see stars orbiting around black holes, massive black holes. Now, these orbits, even though you saw it kind of zip up really quickly as if it was getting close to the massive black hole, these are actually quite weak field. So the closest known star, the star that's closest to the big black hole, is about 400 times the mass of the big black hole in geometrical units at its closest approach. Even at that significant distance, it's already moving pretty fast, about 10% of the speed of light. But in terms of strong field GR, it's very weak field. So these MRIs I'm talking about are much, much, much closer. They're really, really, really zooming in here. So here, as I mentioned, we see about 10 to the 5 orbits in the strong field. And what do I mean by the strong field? Well, these orbits, almost all of them, are within 10 m. So 1/40th the radius of the stars we've seen to date. So these are really probing the strong field regime right around the massive black hole. And they're probing it with incredible precision because you're having so many orbits in that tight regime. So let's see how well this movie plays. So this is an example of an MRI. Here it actually looks kind of interesting because it's slowed down and not working correctly. But it actually allows you to see the geometry a bit more. So compare this with what we saw from the comparable mass quasi-circular binary, where all you're doing is sending out very simple ripples, everything's sinusoidal. This is a much more complicated system. You might have noticed the central black hole getting bigger and bigger with time there. That is not physics, that is the camera zooming in on the black hole. The black hole does grow, but not that much, a very small amount. So these are very complicated systems with a lot richer morphology in the waveform. So these lectures are not about the physics we're going to get out of these systems. These lectures are focusing much more on the theory side. How do we model these systems, and why is that interesting? But just to give a quick list of things we ultimately hope to get out of measurements of MRIs. So first off, they're going to be pretty spectacular laboratories for fundamental physics. Historically, the main thing people discussed that we can get out of measurements of MRIs is tests of the no-hair theorem. Now, of course, you can't really test a theorem, it's a proved theorem. Really what we're testing there is this actually a Kerr black hole, or is it something stranger? And is GR correct, or is the true theory something else? Yeah.
What's the timescale for these orbits in MRIs? Just maybe are we talking years? Are we talking days?
Do you mean for the whole signal or for like one orbit? Oh, for a single orbit. So everything Lisa's going to see is in the millihertz.
Okay.
Yeah. The entire evolution will be in years. Yes, so because the small object is acting as this incredibly high precision probe of the space-time around the massive black hole, we can do precision measurements of the properties of the black hole. For example, we can measure its mass and spin to 0.01% error. That's the estimate. And also the quadrupole moment of the massive black hole, with slightly less precision, but still pretty remarkable precision. And I think this is actually a little bit of a conservative estimate. We can probably do better than that. Now, once you've measured the mass and the spin and even one of the higher moments, you have enough information to test, is this a Kerr black hole or not? because in Kerr, you have this very specific relationship between the mass and spin and all the higher moments. All the higher moments can be written in terms of the mass and spin. So if you just take L equals 2 here for a quadrupole moment, you can just check, does it satisfy this relationship? And if it violates that relationship, well, it's either not a Kerr black hole or, well, actually, no, it's just not a Kerr black hole. That could mean GR is right, but it's some weird object there. People have cooked up lots of possible weird objects called exotic compact objects. Or it could just be that GR is failing on this regime and some other new fundamental physics is coming into play. So along those same lines, we'll have incredibly precise measurements of any new fundamental fields and charges. If GR is slightly wrong, or even if the standard model is slightly wrong, you can have new scalar fields, new scalar charges, and we can measure those with incredible precision with MREs, along with any number of other deviations from standard model, deviations from GR, deviations from the Kerr quasi-normal modes. You can test for presence or absence of an event horizon, etc. And yes. So parameterized post-Newtonian doesn't work for these systems because post-Newtonian doesn't work for these systems. I would like to see, and I said I would do in a grant application, a parameterized, what I'll call post-adiabatic, for a reason that will become clear, parameterized post-adiabatic theory. Because just like in the post-Newtonian limit, the weak field limit, you start to get decouplings between complicated strong field effects. In the small mass ratio limit, the extreme mass ratio limit, you get a similar decoupling. And so you can actually isolate, okay, this kind of effect just appears as a linear term here. This kind of effect appears as a linear term here. And so it should be possible to have a parameterized theory to do these tests. And yeah, these kinds of tests will typically be more precise than any other planned experiment. Of course, it depends on the very specific test you're trying to do. Massive black hole binaries will also give you incredibly precise measurements, but usually of slightly different things. And it's still unclear which will give us the best constraints on violations of GR. Okay, that's all fundamental physics. We also have astrophysics. So as I said, by measuring these systems, we can get a lot of information about the population of black holes in the universe, their history or their evolution over galactic timescales. So in particular, one of the things you can measure is the mass function, the number of black holes with a given mass in the universe. And again, this is kind of unique information you can get from MREs. The more unique information you can get that you really won't get from anything else is information about the stellar environment around these big black holes, so the stellar environment of galactic nuclei. So you can measure things like properties of the accretion disk, or at least we hope we can measure things like properties of the accretion disk. Sometimes, depending on the significance of the astrophysical effect, you can just directly see it in your waveform. Other times, you're hoping to see quite a lot of MREs, and then just doing statistics on their distribution over parameter space, you can extract information about typical stellar environments around massive black holes. And over the last 5 years or so, I've seen in the community a big shift from fundamental physics over to astrophysics in the hope for how much information we can get out of MREs. Partly that's because people started to worry, wait, can we do these fundamental physics tests if there's these environmental impacts? How do we distinguish between a fundamental physics effect and astrophysical effect? So you actually need to think of these two things together at once to be able to disentangle them. With MREs, we can also do cosmological measurements. Again, this is using statistics, building up a catalog of MREs, but you can measure the Hubble constant and measure the dark energy equation of states, just as an example. Yeah. It's not that precise, unfortunately. So we expect to be able to measure the Hubble constant with like 1% precision. So It's a totally, separate, independent source of data, but it's not cutting edge accuracy. Whereas these other things, the astrophysics and fundamental physics, are cutting edge precision. Okay, so in addition to these comparable mass binaries and these extreme mass ratio binaries, there's also things, of course, in the middle. You don't just have things that are either far extreme. So these things are called intermediate mass ratio inspirals, IMRIs. Here, you're imagining the 1 to 100 mass ratio. It's very vague in the literature where comparable mass ends, intermediate mass begins, and extreme mass begins. These are all kind of overlapping to some extent. Generally, IMRIs, here I wrote 10 to the 2 to 10 to the 4 mass ratios. Probably more like 10 to the 2 to 10 to the 3, but whatever. It's all a vague boundary between different systems. The main thing that's distinguishing these is that they involve an intermediate mass black hole. So even detecting black holes on their own in this range is very interesting astrophysically, because it hasn't been exactly clear how black holes form in that range of masses. These kinds of systems are potentially observable by ground-based detectors and space-based detectors, but different versions in each case. So a ground-based detector will see an intermediate mass black hole, like 10 to the 3, or just 150 solar masses or something like that, orbited by a much smaller thing like a neutron star, which is a few solar masses. Space-based detectors will see the more extreme version, where it's a massive black hole orbited by an intermediate mass black hole. And you get different science out of these two different kinds of detections. Okay, so as I mentioned, numerical relativity is struggles with extreme mass ratios. Maybe that's not clear why. But the fear has been that you will not be able to simulate these systems at all, let alone EMRIs, with numerical relativity. And so there's multiple reasons why numerical relativity struggles. And I think I'll explain that a bit more in a second. But what we have seen to date is that the self-force method, the perturbative method, appears actually not to struggle with these kinds of mass ratios. It seems actually quite accurate for these mass ratios. So historically, there had been a fear that no model would be accurate for these systems. I think the consensus is now coming to be, oh no, everything's accurate for these systems. And they're not as hard as we feared. So, self-force theory. Now, why can we not use numerical relativity, and why can we not use post-Newtonian theory? So, as I said, we're looking at highly relativistic systems here. The small body is very close to the big body for a long time. And because it's so close, post-Newtonian theory is not sufficiently accurate. The fields are too strong, and the motion is too fast. Then, in addition to the strong fields and fast motion, we have very disparate length scales, which is very hard for numerics to cope with. So first off, you can imagine, if you have a small body orbiting around a more massive one, the numerical relativity simulation needs to resolve the small scale of the small body and the big scale of the orbit and the waveform that comes out. And if it's 10 to the 5 disparity between those two, that's a big problem. But the bigger problem is actually coming from how that plays into the number of time steps. So first off, these systems take a really long time. You get 10 to the 5 cycles. It's a huge number of cycles for EMRIs. And so the runtime, naively you'd think, then scales with the large mass ratio. So the bigger the large mass over the small mass, the bigger or the higher the number of time steps. But it's actually worse than that, because you have to resolve the small scale of the small body, your time step also has to be small. So what you end up getting is that the runtime for a numerical relativity simulation scales quadratically with the large mass ratio. So if a current system, say 10 to the 1, not 10 to the 1, 1 to 10, a system with a 1 to 10 mass ratio That's really pushing what numerical relativity can do. That would take, a month or a few months to generate. These days, probably a month. So that's got to be multiplied by 10 to the 4 squared to get the runtime to simulate an emery with numerical relativity. So 10 to the 8 months to simulate a single waveform. And as I mentioned, we actually need lots and lots and lots of fast waveforms for data analysis. So it's totally hopeless to use numerical relativity. People are trying to push numerical relativity to higher mass ratios, but not to this extreme regime, more like 1 to 50, 1 to 100 maybe, but that's really pushing it. So what do we use instead? Well, we need something that is accurate to much less than 1 radian of error in the gravitational wave phase, because the data analysis relies on tracking the phase very accurately. That's how you make your detection. That's how you do your science. So we need something that's has much less than 1 radian phase over this huge number of cycles, 10 to the 5 cycles. And so many ways you might try to implement this would accumulate little errors that would keep getting bigger and bigger and would be a disaster. So we need a very specific method that can do this. And that method is gravitational self force. So think about when you first learned GR. One of the fundamental things you learned is that if you put a little object into a space-time, it moves on a geodesic. So we'd say, if it's a test mass, it moves on a geodesic. That's a fundamental principle of GR. But that's actually just an approximate statement. In the limit, where you're considering something that's sufficiently small and sufficiently light that you can ignore its effect on everything else, and then it does move on a geodesic. But once you put a real physical body into a space-time, it's not going to be moving on a geodesic of the external space-time, because it's going to be influencing the external space-time. So if we consider a real physical body, it will perturb the space-time, and we can write some kind of expansion like this. So here, I'm writing the exact space-time on the left. I'm doing a series in the small mass ratio. So epsilon here is small mass over big mass. And so this background, in the case of an emery or in the case of a binary, the background space-time is the space-time of the larger body if it was just sitting there on its own, unaffected by anything. So this, for us, will generally be a Kerr metric. So we have Kerr plus perturbations. So we have a first-order perturbation produced by the small object, second order, and so forth. Now, this deformation of the geometry around it acts back on the small body and influences its motion and causes it to deviate away from geodesic motion. So here I'm writing on the left the covariant acceleration in the background, in the external background spacetime, so the Kerr metric of the big black hole. So if you had geodesic motion, like for a test body, well, for a test mass, on the right you just have 0. So here we're looking directly at corrections to geodesic motion, corrections to test particle motion. Now, the reason I corrected myself from saying test body and switched that to test mass is that you also have finite size effects. So on the right-hand side, you don't just have effects coming from the deformation of the geometry, you have effects coming from the extended size of the small object coupling to the external background curvature. Those will both come in with powers of the mass ratio. So even if it was a test body that wasn't perturbing the spacetime around it, it still wouldn't move exactly on a geodesic. But this whole method I'm going to introduce, one of the outputs of it is it actually provides a derivation of the geodesic principle at leading order in this perturbative scheme. Okay, so as soon as we write down some kind of expansion like this, you immediately have to ask, how high order do we need to go for the science we're interested in? How many orders in epsilon do we need? So there's a very simple scaling argument that tells you. So first, the force is small, Everything on the right-hand side is small because it comes with powers of epsilon. And we're going to argue that the order we need to go to is exactly second order, probably not higher, depending on what system we're looking at, but definitely not lower. So the inspiral occurs very slowly because the perturbing force is small. And as I said earlier, the evolution of the system is on this time scale 1 over the small mass ratio. Now suppose that we neglect this second order term. So we have an error in the acceleration. This is of order epsilon squared. If you just naively integrate twice with respect to time, then you get an error in position that's of order epsilon squared times tau squared, where tau is the overall time you're looking at. So if we're interested in a time scale 1 over epsilon, and we plug that in here, the epsilons cancel, and we get an order 1 error in the position of the small body. And we need the errors in the gravitational wave phase, and therefore in the motion of the system. We need those errors to be much smaller than 1 radian. So if we have an order 1 error, that's unacceptable for gravitational wave modeling. But it's actually potentially worse than that because you don't know what the coefficient is in that term. The coefficient could be 10, it could be 100, it could be anything. So you need to control this term before you can be confident in your model. So that is the goal of the self-force community over the past 20 odd years, calculating everything in this perturbative scheme through second order in the mass ratio. Now we can get a more, yeah.
Is it that this perturbation is actually converging, or stay on the first few terms?
So we don't know. We can see the asymptotic convergence rate by comparing to things, which I'll show you in a second. We don't know if it's actually a convergent series. Even if it is convergent, it's unlikely it will converge exactly to the correct answer because it can never capture things that are exponentially suppressed. And so some things, like, for example, the quasi-normal mode ringing of the small object, those are exponentially suppressed with respect to this parameter. So if you're just doing a series like this, you'll never recover something that's exponentially small. I don't know if it's actually convergent, but it definitely has the right properties in terms of asymptotic convergence, not convergence. Yeah, it's behaving correctly in the asymptotic limit. We don't have things blowing up. You can formulate things so that things do blow up, which is bad, but that's not what I'm going to describe here. Okay, so in order to understand the behavior of this perturbative scheme, and in order to get a more precise scaling estimate for what order we need to go to, let's start with 0th order. So in 0th order, we just have a test mass on a geodesic in Kerr spacetime. So just the test mass is already very complicated motion. This is non-trivial, but it is integrable. So a geodesic in Kerr has 3 constants of motion: the orbital energy, coming from the time-like killing vector of the Kerr metric, the azimuthal angular momentum. So this is angular momentum around the vertical axis in this image, and that's coming from the axially symmetric killing vector. Then there's this kind of hidden constant called the Carter constant, and that is related to orbital inclination. So these, unlike orbits in Schwarzschild, or unlike geodesics in Schwarzschild, geodesics in Kerr are not confined to a plane. They move in and out of the plane. The whole orbital plane precesses, bobs up and down. And the value of this Carter constant, which comes not from a killing vector symmetry, but from a killing tensor symmetry, the value of the constant tells you what is the maximum inclination of this bobbing. It goes between a maximum like this. So, mentioned, it's bobbing up and down, and we have a specific period of that bobbing. But we have 2 other periods. So these systems are called triperiodic. We have 3 periods. So you have the polar period of this precession of the orbital plane. you have just the azimuthal period for the azimuthal motion around the z-axis, and you have a radial period, because if you have eccentricity, you have a separate period for motion in and out radially. So we have three distinct periods. Now, for each of these periods, we can construct phases that go from 0 to 2 pi over one oscillation. So 0 to 2 pi over one polar, 0 to 2 pi over one radial, and 0 to 2 pi for one azimuthal orbit. And you can construct them such that they have constant frequency. So they're just linearly growing, exactly linearly in time. For people who've studied, Hamiltonian mechanics, these are action angles. So these have exactly constant frequencies, and these three frequencies are uniquely determined by these three constants of motion. So you specify energy, angular momentum, and Carter constant, and then you can calculate these three independent frequencies. Now that's just the 0th order case where you're ignoring the effect of the small body's gravity and the effect of its finite size. So what happens when you turn on the self force? So self force is just whatever is on the right-hand side of that now accelerated equation. So it's replacing what was 0 in the test mass limit. Once you turn on the self force, these things that were constants of motion are now going to be evolving with time. Things are going to be changing. You're not going to have these constants because you don't have these symmetries in your perturbed spacetime. But they're all going to be evolving slowly with time because the whole system is evolving slowly compared to the orbital timescale. So we have two distinct timescales. We have what is called the radiation reaction time. That's the 1 over epsilon I mentioned before. So that's the timescale over which the energy changes appreciably. Then we have the orbital time, which in terms of epsilon is just epsilon to the 0, because that's determined just by the background mass. It's not determined by epsilon at all. Now, if we wait this long time, what was first shown by Hinder and Flanagan is that those three orbital phases have an asymptotic expansion like this. So here we're expanding in powers of epsilon, and the coefficients are dependent on epsilon times t. That's because we're interested in this long time scale, 1 over epsilon. So if t is 1 over epsilon, then epsilon times t is just of order 1. Now here we start with a singular power of epsilon, start at order 1 over epsilon. That's because we're waiting a long time that's of order 1 over epsilon. So the number of cycles, or the amount of phase you've accumulated, is roughly order 1 over epsilon, because things are changing roughly linearly in time. Then you have corrections to that, come at epsilon to the 0, higher order corrections, epsilon to the 1, etc. So this gives us a more precise scaling estimate for what kind of accuracy we need in our model to correctly track the phase. So these are the orbital phases, but those almost directly give you the gravitational wave phase. So we can base our estimate just on the orbital phases. And the idea is, okay, clearly you need this leading term, otherwise you're going to be off by something enormous. So the most important thing is to get this leading term very precisely. You then need this next term because it could be 1 radian, which is already bad enough to mess up our science, or it could be 10 radians, it could be anything, because scaling is independent of epsilon. So we definitely need these first two terms, but the argument is we don't need the next term or any higher terms, because for sufficiently small epsilon, it's going to be negligible because it scales with power of epsilon, positive power of epsilon. So for mass ratio 10 to the minus 5, even if it happens to come with a really bad coefficient, 100, it's still tiny, still totally irrelevant. And I'll show you evidence that is not a factor of 100, it's a much smaller coefficient than that. So we think getting these two terms, leading and subleading, is necessary and sufficient to get exactly what we need for gravitational wave science. Yeah. Yeah. Mm-hmm. So the phase is changing roughly linearly in time. That's why I'm having a 1 over epsilon. Yeah. So we'll deal with that very extensively later in the lectures. The point is it's slow though. It's much slower than the change of the phase, the rate of change of the phase. But yeah, the whole third lecture will be about that, so we'll get back to that. Okay, so Hinder and Flanagan came up with this nomenclature. They called this leading term adiabatic order. So this is just capturing slow evolution, nothing else. And it's only capturing that slow evolution at leading order. And they showed that you can get this term just from the averaged dissipative piece. So if you define a particular average, and you need the average of the dissipative piece of the cell force, so the first order cell force. So it's basically the average rate of change of the energy, average rate of change of the azimuthal angular momentum, etc. So you don't even need the whole first order cell force, you need a particular piece of it. Then for this next term, we call that first post-adiabatic order. You'll hear me referring to this as 0 PA, 0th post-adiabatic order, and this as 1 PA, first post-adiabatic order. So for this, we need more dissipative information. Now we need the averaged dissipative piece of the second order cell force. So we need to go to second order in perturbation theory. And we need all the rest of the first order cell force. So the cell force includes conservative effects, not just dissipative, and includes oscillatory effects, not just secular averaged effects. So this is what we need to get the accuracy that we're aiming for gravitational wave astronomy. We need to do second order perturbation theory, but we don't need everything from second order perturbation theory because we only need the averaged dissipative piece of the second order cell force. Okay, now we had a question about how does this converge, what's the accuracy, and I gave you scaling arguments, but you need to know the coefficients. You need to know, are the coefficients getting huge as you go up in powers of epsilon? So the first test we really had of this, so here what I'm showing you is the rough schematic transitioning into an actual numerical assessment of how accurate these different models are. So this was done by Martin van de Ment and Harold Pfeiffer a few years ago. And so remember we had cell force in the bottom right. That's being replaced here by a 1 PA model in this pink band. We had post-Newtonian theory at the top, that's in green up there, and then numerical relativity in the bottom left. And so what you see here is that a 1 PA self-force waveform actually covers a really surprisingly large amount of this diagram. So this range of mass ratios is only going from 1 to 1 up to 1 to 40. So nowhere near an Emery, but you're already seeing self-force covering a big band. Now, I should say this was a prediction. What this comes from is they took a whole bunch of numerical relativity simulations, and they did a small mass ratio fit. They just guessed that the phase is a series in mass ratio of the form I showed you before. 1 over epsilon times the coefficient plus epsilon to the 0 times the coefficient. And that's where they came up with these estimates. That's where they got these estimates. And we've since found that their estimate was a bit overly optimistic on this side in a really equal mass regime. But once we get down around here, it was actually a very solid estimate. And so we now actually have the real 1 PA waveforms, and I'll show you those now. So this was the first 1 PA waveform that ever has been generated. So I did this with collaborators a couple of years ago after 10 years of concerted effort. So here what I'm showing you is 1 PA, so second perturbative order, a 1 PA waveform compared to a numerical relativity waveform from the SXS collaboration. So for our purposes in this comparison, we can think of the numerical relativity waveform as just exact. And we're just testing how well do we reproduce it. This is for mass ratio 1 to 10, so very far away from the Emery regime. And you see, so what we've done here is we've matched the phase and frequency at the earliest time we can. the earliest time that the numerical relativity data is reliable, and then just evolved forward and looked at, okay, how well are we reproducing the phase and amplitude? And so you see where we cut this off, we're off by 0.3 radians or something. But most of that dephasing actually happens quite late. So people who knew about different modeling methods, a lot of them, okay, there's different camps. Some of them thought, wow, this is amazingly accurate. I thought this was an Emery model. People from self-force were less amazed because you have a quantity that's 1/10 and you have an error in your phase that's 1/10. So it's actually almost exactly what you would have just naively guessed. Now, the reason this stops here and doesn't go through the full merger is we're using a particular type of expansion in epsilon that breaks near the end. The expansion is no longer valid right near the end. So we're working on developing new expansions that go through all the way to the end, but that's a work in progress. Okay, so over the remaining lectures, I've given you a whirlwind tour over the remaining lectures. We're kind of going to build up from the underlying foundations to arrive back in this waveform, so you have some understanding of the methodology that led to this. Okay, so I've been speaking for an hour, and I was told we should probably have a little break before the next bit, so maybe 5 minutes. Okay.
A way to understand which these calculations are visible, which are just the gauge mark. Basically, when we expand the metric, not all of the metric calculations are visible. So we have to take into account when we start performing all this.
So yeah, gauge is a big topic in self-force. Ultimately, you calculate a waveform that's gauge invariant, but the intermediate calculations, gauge is an enormous headache, and you need to be very careful about your choice of gauge. Ultimately, yeah, you calculate some invariant quantity that's insensitive to what you did in the middle. I don't know how much I'll talk about what gauges we pick, but I will have some discussion of gauge in this lecture. Yeah.
So you mentioned at some point that also finite size
Yep.
change the answer. So what's their size in comparison to self-force corrections?
So for the systems we're interested in, we always assume we have a compact body. And so you have a very simple scaling. It tells you how a multiple moment scales with the mass of the body. And it's, I'll actually show you exactly where, for example, the spin comes in. But at each new perturbative order, you get one higher multipole moment of the small body. So in this small mass ratio limit, fine intrinsic details of the body go away, and everything's encoded just in multipole moments. And yeah, I'll show you how they come in. Okay, so far I've given you just a big impressionistic overview of the field. Now this lecture, I'm going to get into the mathematics. So I'm going to break up self-force theory into what I'll call the local problem and the global problem. So by the local problem, what I mean is, how do you deal with the physics right around the small body? You're just putting some small body into the space-time. How do you deal with that? Then the global problem is, okay, I've got some small body. I understand what's happening near it. It's now orbiting around the big body. How do I solve the Einstein equations in that setting? So I'll cover the first half of that, hopefully. Okay, I'm probably not going to get through all of lecture 2 today. I'll see how far I can get. So I'm going to start off with just general overview of perturbation theory in GR. So very often when students are starting out, they learn linearized theory and are given no idea, okay, what happens beyond linearization? What happens at higher orders? So I'll explain that not in a lot of detail, but a little bit of detail. I'll then explain what we do once we put a small body into the space-time, introduce this concept of punctures, where we're really throwing away irrelevant details about the body and just encoding everything in a singularity. I'll then relate that to what we mean by a point particle and something called mode sum regularization. Okay, so let's start with just perturbation theory in GR. So the first thing we need to do is derive what the Einstein equation looks like when you perturb around some background. So I'm going to write the exact metric and associated quantities with a hat. So G hat is the exact metric of the full spacetime. For almost everything I'm going to say in this lecture for the rest of the morning, I'm not just focusing on a binary system. I'm not focusing on an emery. I have a small body in some spacetime. I don't care what it is. So I'm just saying, let's take the exact spacetime of that system and split it into some background, G with no hat. So sorry for the change in notation. I used the sans serif G for the exact metric a few slides ago. I'm going to be using hat for the next little while. And then here, I'm adding some perturbation. Now, the H here is not a linear perturbation. I'm just defining H to be the difference between the exact spacetime and the background spacetime. And now the way you derive the perturbed Einstein equations is you look at the difference in the Christoffel symbols between the exact spacetime and the background spacetime. So of course, the Christoffel system associated, not Christoffel system, Christoffel symbol associated with a particular metric is not a tensor. But if you take the difference between two Christoffel symbols, then you do have a well-defined tensor. So we call that capital C. I'm following the notation from Wald's textbook here. So we have some capital C, and it turns out with a very short calculation that I can write a simple formula for that. Somehow this pointer is even worse than it was before. Maybe if I point over there. No, hopeless. Okay. So it has a very simple formula in terms of the inverse of the exact metric, and then some derivatives of the perturbation. So nabla here is the covariant derivative associated with the background metric, not with the perturbed metric. We have a simple formula here. And once we know the corrections to the covariant derivatives through this, well, then we can write down what the Riemann tensor is in the exact spacetime in terms of this tensor C. So we have zero torsion, we're in GR. So the Riemann tensor is just the commutator of the covariant derivatives on the exact spacetime. So we just write these covariant derivatives in terms of the background Christoffel plus this capital C, rearrange, and you have a nice simple formula telling you the Riemann tensor of the exact spacetime in terms of the Riemann tensor of the background and this capital C tensor. So in the Einstein equation, we just have the Ricci tensor. So we contract two of the indices, and we have a nice simple formula for the exact Ricci tensor. So here there's no approximations. All I'm doing is writing curvature tensors on the exact spacetime in terms of background stuff and stuff involving H. So a very simple formula in terms of the correction to the Christoffel symbols. Now, before expanding in powers of some small quantity epsilon, I'm going to expand in powers of nonlinearity. So that capital C involved the inverse of the exact metric. And if we take the inverse of the exact metric and expand it in powers of H, you get a simple formula like this, where now on the right-hand side, indices are being raised and lowered with the background metric. So always when you're raising and lowering with the background, not with the perturbed metric. And so you can just easily check this is in fact, yeah.
Because it's just right?
It's the binomial series, yeah.
Oh, it's the Neumann series. It's just like alternating sums with like powers in H.
I'll check that after. I think this is right. Yeah. Okay, so we now plug this expansion into that capital C and expand out the capital C in powers of h, and then plug that into my expression for the exact Ricci tensor. And we then get an expansion of the Ricci tensor in powers of the perturbation h. The first term, R1, is just the usual linearized Ricci tensor, which hopefully everyone has seen before. So it's just a simple linear operator acting on h. And there's different ways people write it. This is a common way that I'm going to be referring to as we go forward. Basically, here we have a wave operator. This is the curved space D'Alembert, plus a curvature term, plus this thing that is the divergence of h bar. H bar here is the trace reversed perturbation, which is h minus a half g times the trace of h. So h bar, if you take the trace of h bar, you get minus the trace of h. I'm not going to bother writing down the quadratic piece of the Ricci tensor, but it basically has this structure where we've got derivatives of h squared, and we've got h times second derivative of h. So every term has two derivatives and two powers of h. So as we look up here, we've got a linear term in h, a quadratic term in h, you'll have a cubic term, etc. Now this is just an expansion in powers of nonlinearity, but ultimately we're interested in systems with some small parameter. So let's consider a one-parameter family of spacetimes where the exact metric is a background plus a perturbation. And similarly, let's assume we have a stress energy tensor that depends on some small quantity epsilon. So epsilon here doesn't have to be small mass ratio in a binary. This is just a totally generic framework. So we had an expansion in powers of nonlinearity. Now let's expand h in powers of epsilon and substitute that into the expansion in powers of nonlinearity. So now what you're going to get is a background term plus the usual linearized Ricci tensor constructed from the first order perturbation. Then at second order, you have another linear term, but now constructed from the second order perturbation. And then we have this quadratic term that's quadratic in the first order perturbation. Similarly, we're going to write down an expansion for the stress energy tensor in powers of epsilon. Now, once we've expanded everything in powers of epsilon, we can look at the Einstein equation. So the left-hand side of the Einstein equation is just the trace reverse of this, effectively. And the right-hand side is just the stress energy tensor. And we just equate we equate coefficients of powers of epsilon. So we look at the linear term in epsilon, we equate the coefficients. We have the linearized Einstein equation here. G1 of H1 is equal to T1. So that's just the usual linearized Einstein equation. Then at second order, on the left-hand side, we still just have a linear operator acting on H2. I'm moving quadratic effects to the right-hand side. So on the right, I have T2, the second order term in the stress energy. And then I've moved quadratic stuff like this just to the right-hand side. So what we have is, well, first we have a fully nonlinear background equation, but we're assuming we're just given the background metric that satisfies that equation. Then we have a sequence of linear equations. So we have a linear equation for H1, where we have some source. We have a linear equation for H2, but now in addition to a material source, it's now being sourced by things that are quadratic in H1. So this is the structure of the Einstein equations we're trying to solve, a sequence of linear equations like this. Now, as we briefly mentioned a few minutes ago, perturbation theory in GR comes with gauge freedom. H, the entirety of H is not gauge invariant. So there's two different ways of seeing what this gauge freedom represents. The simple way is infinitesimal coordinate transformations. So, GR is diffeomorphism invariant. We can choose whatever coordinates we like. We can apply any coordinate transformation we like. And in the case of a small epsilon expansion, you can in particular have these near identity transformations. So you change from some coordinate system x mu to a new coordinate system x prime mu that is almost x, well, you have order epsilon corrections with some vector field C. Now, we expand the metric in these two different coordinate systems. So this is the same physical metric, but just in different systems, different coordinates. So we have g hat with no prime in terms of the coordinate x, and we have g hat prime in terms of the coordinates x prime. So in both cases, we're just expanding in powers of epsilon at fixed coordinate values. Then we can relate these two just using the standard tensor transformation rule for how the components of the metric transform. So g prime here is just the usual Jacobian times g. Also think of this as the pullback of the transformation. So let's take this tensor transformation rule, expand x as a function of x prime. So if we take this equation and just move the c to the left-hand side, then we have the old coordinates in terms of the new ones. X as a function of x prime. And that's what appears inside the metric on the right-hand side here. X is a function of x prime. And similarly in the Jacobian, you're taking derivatives of x with respect to x prime. Expand everything out, do a little bit of very simple manipulation, and you get this form. G prime at x prime is equal to the old g, but now just evaluated at x prime, so it's just at the same coordinate position as on the left-hand side, is equal to h, which was the perturbation in the unprimed coordinates, plus this Lie derivative along the vector field xi. The vector field xi was introduced back up here as my small transformation. So this line here has to be equal to this, right? Because it's of the form, I'm expanding in powers of epsilon at fixed x prime. And so what we find is the usual thing. Hopefully, everyone has seen this, at least in the case of perturbations of flat spacetime, maybe also in the case of perturbations of a generic curved background. What we find is that h prime, the perturbation in the new coordinate system, is equal to h plus this Lie derivative. Yeah.
That's really, I mean, it's just a question of wording, I think. Does it really make sense to call these order transformations if we don't transform background measurement?
Yeah, because I'm just using the coordinate transformation rule here.
But not for background, because you don't put it.
No. This is, I'm transforming the background. That's exactly.
No, but I mean, in the expansion, you subtract the background, the same background coefficients, just evaluated at the positions, right?
Yeah, so that's just the effect of having a near identity averaging, not averaging, near identity transformation. So I'm doing the simple case where the coordinates only differ by epsilon. If you do the more general case, you'd have some function of x in that top expression, and then the background will get transformed. Yeah. Yeah. So we have the full range of diffeomorphisms here, background diffeomorphisms, and the perturbative ones. Yeah. Okay, there's also a more geometrical way of looking at this, which is my preferred way, and it's the more efficient way once you go beyond linear order, but it can be confusing at first. So let's think about what we're doing geometrically. We have a family of spacetimes, right? For each value of epsilon, we have a new spacetime. So let's just stack those up. So here we have epsilon running vertically. And so each value of epsilon gives us a new manifold with a new metric. The base manifold down here at the bottom is the background spacetime manifold. And then what are we doing when we're expanding in powers of epsilon at fixed coordinates? Well, geometrically, what we're doing is we're saying, okay, we're trying to approximate the metric up here in terms of things evaluated down here at the bottom. And well, the only way to do that is you have curves going from the top down to the bottom. A family of curves, you're following a family of curves and doing a Taylor series along those curves. So here's just an example of one curve. where we're going from a point P in the background manifold up to point Q in the perturbed manifold. And the way to write down this Taylor series in powers of epsilon geometrically without choosing any coordinates is in terms of a pullback. So I mentioned in the previous slide that we were looking at a pullback. So we have some map from P to Q induced by the flow of a vector field, capital X. We expand this pullback. So what we're doing is we're taking fields at Q, pulling back down here to fields at P, and expanding those out in powers of small epsilon. And then you get everything in terms of Lie derivatives. So you have metric evaluated at P, plus a Lie derivative along this curve going up, just like an ordinary Taylor series along a curve in 2 or more dimensions. Then the higher order terms are epsilon squared times a half the second derivative. And it's just an ordinary Taylor series, but now in terms of Lie derivatives. Now, I find this very useful just to, when you're dealing with complicated calculations, just to think about what gauge is actually meaning here without having to introduce any coordinates. It also gives you a simple way of deriving gauge transformations. So H1, where we've expanded along this curve on the right, H1 is the linear term in this expansion. So it's the Lie derivative along that curve going up. Choosing a different gauge means you're just choosing a different path up through this family of manifolds. And so then this is generated by a new vector, y. So in my new gauge, my linear perturbation, H1, is a derivative along this new vector, y, going up to this new point, Q prime. So if we're looking at the difference between H1 in the new gauge versus H1 in the old gauge, well, all it is the difference between these two Lie derivatives. That can be combined to a single Lie derivative. And then we just call y minus x this vector field xi that I introduced in the previous slide. So this is essentially a one-line derivation of the gauge transformation rule. And you easily get this for a tensor of any rank. It's not restricted to a metric. And in particular, this method is much quicker to derive higher order formulas, second order and beyond. Okay, now a gauge that I'm going to refer to a lot is called the Lorentz gauge, named after the similar gauge in electromagnetism. So I mentioned this field H bar, this is the trace reversal of H. The Lorentz gauge condition is that the divergence of H bar is 0. Just like the Lorentz gauge condition in electromagnetism is that the divergence of the electric potential is 0. Now, if you impose that, then the linearized Ricci tensor becomes very simple. It's just this D'Alembert of the background plus a curvature term. And the relationship between Ricci tensor and the Einstein tensor is also very simple. Sorry, here I'm restricting to a vacuum background, whereas previous slides I had allowed for a stress energy. This is vacuum background. In that case, to go from Ricci tensor to Einstein tensor, all you do is put a bar on top of H. So the trace reversal is very simple. This gauge historically was very useful in the self-force context. So I'll be using that quite a bit. Okay, everything I've said so far is just generic perturbation theory. Doesn't involve a small body in particular, it's just totally general. Now let's focus on the case of a small body, analyze how we want to deal with that. So we're taking some totally generic space-time and plopping a small body into it. I'm going to restrict my attention to compact objects, meaning that the mass and spatial size of the object are comparable to each other, and both comparable to my small quantity epsilon. So epsilon here, as I said, for a binary system is small mass over big mass. For a totally generic external background spacetime, epsilon here will be small mass over just whatever external length scale is convenient. So here is some blob of either matter or whatever, it could be a black hole, moving up in time. How are we going to deal with it? Well, the naive approach, the first approach you might think of is just, okay, put a small body into Einstein equations, see what happens. So that's very complicated because you have to deal with whatever internal degrees of freedom the body has. You'll get a totally different problem for a material body than you would for a black hole. You get steep gradients in the metric near the small body. So it's very complicated. And this is effectively what numerical relativity would have to do if they're just directly solving the fully nonlinear Einstein equations with a small body in the space-time. So that's not what we're going to do. Here's another option. Say, okay, I don't care too much about the fine details right where the body is. What I care about is, how it's moving in the external space-time and what are the gravitational waves that come out. So you could say, okay, let's restrict the problem to, large distances compared to the size of the small body itself. Those distances can still be very small compared to external length scales, but just big compared to the body. And then on those bigger length scales, you can treat your small mass as a source of perturbations of the external background, just like I showed in previous slides. So we're just ignoring this region right around the body and saying, okay, we have external background plus perturbations due to the body. But then you need some kind of boundary condition on this surface that you removed. So you can imagine, okay, let's impose the condition that the metric in this region must agree with the metric outside a small compact object. And let's derive that metric in some appropriate way. So this is something like a free boundary value problem, because the whole motion of this tube is affected by the perturbations outside the tube, and you're imposing some condition on the surface of the tube. And so you have a boundary value, something like a boundary value on the tube, but the location of the tube is responding to your solution. So this is a hard problem to tackle. Although I should say that with collaborators at the AEI, actually am tackling this using full numerical relativity with an analytic solution inside the tube. So that is one viable way to go. But I assume we're almost all physicists in here. And if you're a physicist, you'd think, why do I care about any of this? Just make it a point particle. That sounds like a warning of some kind. I'll assume that's okay. Okay, so yeah, you can say, what do we do in physics ordinarily if we have something small? We just say it's a point particle. So physically what's happening is, say you had that surface that we, surrounded the black hole with, or the small body, and we said, let's somehow figure out what the metric is in the vicinity of that little tube, and then solve the problem outside. Here what's happening is we're saying, okay, let's take the metric in that vicinity, throw away the body that's inside, and just analytically extend the solution from outside. So think of just Newtonian physics or electrostatics. You have some charge distribution, and if it's perfectly spherically symmetric, when you're taking a point particle approximation, what you're doing is you're saying, okay, let's look at the field outside that distribution, which is 1 over r. Throw that away and just take that 1 over r all the way down to r equals 0. That's the point particle approximation. And that's problematic in GR because GR is nonlinear. So let's say we tried to do that. The leading order metric perturbation, H1, is basically like a Coulomb field in the vicinity of the small particle or the small mass. So it's behaving like 1 over distance from the body. So if we take that 1 over distance, throw away the body, and just extend the 1 over distance all the way to some representative world line at 0 distance, we get a 1 over distance divergence. So here, S is some kind of measure of distance from the body. At linear order, that's totally fine. It's perfectly fine to have a singularity like this at linear order. And we'll get back to kind of proving it's okay a bit later. At second order, it gets a lot more complicated. So at second order, we have this linear equation, but we have a quadratic source term on the right-hand side. So let's say H1 is this 1 over S divergence, or it contains this 1 over S divergence. And let's put that into the quadratic source term here. So I mentioned the form of this quadratic term is basically a square of a derivative of H. So if H is 1 over distance, I take a derivative, it's 1 over distance squared. I square that, I get 1 over distance to the 4. So this is definitely not locally integrable. If I just try to integrate over it, I don't get anything, I get infinity. And also, it's very hard to interpret even in a distributional sense. So it's very hard to make sense of this as a source term in a PDE. Now, there has been work that I've done recently showing how you can interpret it mathematically rigorously, but it's quite subtle and a bit hard to do. So if you just approach it naively and you just say I have a source that is diverging this strongly, then there's just no solution to the equation. The equation has no solution. And you're done. It's all over. So what are we going to do instead? So I mentioned if we excise some region around the body, then we get something like a free boundary value problem. I'm going to take that free boundary value problem, and I'm going to convert it into a different problem. Using, again, the same idea that you have when you're using a point particle approximation, you're taking the local field outside of your extended body, taking its analytical form, and just allowing that to go all the way down to some representative world line where it diverges. So that overall philosophy, that overall method, you can show is mathematically valid here. And in certain ways, it reduces to the standard point particle picture, particularly at linear order. And that's the method we're going to use here. We're going to build up an approximation at some distance outside the small object. And we're going to allow that approximation to extend all the way down to some representative world line for the object. And it's going to be singular there, but we're going to be putting that singularity in by hand in such a way that we know exactly how to work with it. Okay, so the picture I'm going to give here, you can develop a very similar picture based on effective field theory. Yeah. So we don't actually throw away the singularity in that sense, but you can develop a framework that is in spirit quite similar. You have different scales involved in the problem, and you deal with them in some way or another. That hasn't been pushed very far in the cell force context. Really only one person ever looked at that. But the overall picture I'm going to describe is very similar to that. Yeah. Okay, so the reason it's very similar is that we're using this method called matched asymptotic expansions. So the idea here I'm looking at a binary, but again, it doesn't have to be a binary. It can be any space-time containing a small body. The idea is, if we zoom in on a region around the small body, then we can actually identify the different scales in the problem and different regions associated with those scales. So out in the external universe, you're looking at distances of order the external length scale that is, insensitive to the small body. So let's call that the external universe. In this little region, I'll call the inner region, we're looking at scales comparable to the size and mass of the small body itself. Now, the idea is this perturbative expansion I've described, and where I'm expanding in powers of epsilon, is okay in the external universe, but it fails in this inner region. The reason it fails is it's assuming that everything is a small perturbation of the external background. If you're this close to the small body's gravity is way stronger than the external background. So the small body is actually the dominant source of gravity in this little region. So in this inner region, we develop a different expansion called an inner expansion, where now the small body is providing the background space-time, and we're looking at perturbations of that. So this method is well known in GR, but originally comes from fluid dynamics, or if you studied singular perturbation theory, it's a standard method in singular asymptotic problems. So we then have two different expansions, one at some significant distance from the small body, and one that's right near the small body. And we're going to find that you don't actually need much information about that expansion very near the small body. Really, what you need is to determine just exactly the information that comes from the inner region out into the external universe. So in this buffer region in between the two regions, you can kind of think both approximations are okay. You're significantly far from the small body, so you can use this expansion in the external universe. But you're close enough where this inner expansion also works. So in this buffer region, you can take information from the inner expansion and feed it out into the outer expansion. And it turns out that not much information actually feeds out. You don't need to get that much information from the inner expansion. Now, how does the inner expansion work? It's basically just a new expansion powers of epsilon in terms of different coordinates. Coordinates that now are zooming in on the small body as epsilon goes to 0. So we just introduce scaled coordinates where the distance from the body is now scaled by 1 over epsilon. So this S tilde is of order 1 when S is of order epsilon. And now we just do perturbative expansion in the limit as epsilon goes to 0, holding S tilde fixed. So kind of physical intuition here, what's happening is in the outer expansion I described before, you're thinking of, okay, you're keeping some external length scales fixed, and you're letting your small body go down towards 0 size. That's epsilon goes to 0 limit. Here we're saying we're going to take the same limit, but now, rather than the body going to 0 size, the body is going to stay fixed. All the external length scales are going to go out to infinity. So let's say this is my space-time in the vicinity of the body. This little red jumble in the middle is representing some body. It could be a black hole. Well, here it can't be a black hole because it's finite curvature, but in general, it could be a black hole or a material body, it doesn't matter. That buffer region I mentioned on the previous slide is again indicated in orange. So that's significantly away from the body, but still close to the body relative to external length scales. And when I take the epsilon goes to 0 limit, holding fixed basically the size of the small body, I'm just zooming in on that region that's inside or that's enclosed by the buffer region. So the buffer region is getting sent out towards infinity as epsilon goes to 0, and I'm just zooming in on the small body. Now, the reason, or one reason this is useful and the way we can determine what information feeds out from this expansion out to the outer expansion is that in this limit, what you get is an asymptotically flat background spacetime. So the background spacetime in this limit is going to be the metric of the small body as if it were isolated, not interacting with anything. And what you find is that it's always going to be asymptotically flat, just at the background level, just because it's an isolated body. Then what you can do is you go out to infinity in this expansion, meaning just the buffer region, because I've sent that buffer region out to infinity. You can go out to that infinity, and you can measure multipole moments of the space-time. And it's going to be those multipole moments that feed from this inner expansion out into the outer expansion. And that's going to be the only information that feeds from the inner expansion to the outer. Just the multipole moments of the body. Now, this also gives you a way to identify what you mean by the world line of your small body, even if it's a black hole, where you'd think it would make no sense to have a world line inside it. But the idea is, in that buffer region, we need these different expansions to match each other in an appropriate way. And I'll say a bit more about that in a second. By the way, how much time do I have left?
15 minutes.
15 minutes. Okay, so I'm not even going to get close to finishing this lecture. I'll have to think about how to speed up the rest tomorrow. Okay, so in this buffer region, both of our expansions are supposed to be valid, and so they're supposed to agree with each other in a suitable sense that I'll explain in a second. Now, in the outer expansion, when your small body is shrinking down towards zero size, what you're left with is some smooth external space-time with a world line in it. The world line is just like the residual, the leftover from the body shrinking to zero size. And the way we choose an appropriate world line is by looking at the metric in this buffer region. So over here, we can write the metric in coordinates that are centered on this world line. I'll say a bit more about those coordinates in a bit. You have co-moving coordinates moving along with the world line. And then we want this world line to be representative of the motion of the body. So how do you insist that it's representative of the motion? Well, we can read off multiple moments down in this space-time. And one of the multiple moments we can read off is the mass dipole moment. Mass dipole moment is telling you where the center of mass is relative to the center of coordinates. So if you have a non-zero mass dipole moment, that's telling you that your center of mass is not at your center of coordinates. And I said my coordinates are centered on this world line up here. So I want the mass dipole moment to be zero, such that the center of mass of the body is on that world line. In this sense that emerges from this matching procedure. Yeah.
That's a quick clarification. So the zoomed in the region is asymptotically flat
only at first order, yeah. Or sorry, zeroth order, yeah. So yeah, this is cleanest when the mass dipole moment first appears. Gets a little bit tougher at higher orders because you lose asymptotic flatness of your perturbed spacetime. Okay, so we have some notion of a representative world line for the body based on setting its mass dipole moment to zero. But I said that comes from some notion of how these things are supposed to match each other. These two expansions are supposed to match each other. So what is the actual matching condition that we're going to use? Okay, so I have this outer expansion. I'm going to suppress dependence on every coordinate except something that's measuring distance from this representative world line, this distance s. So the outer expansion in this coordinate system that's moving along with the world line, the outer expansion is expansion in powers of epsilon at fixed s. The inner expansion is an expansion in powers of epsilon at fixed s tilde, which was s over epsilon. So here we have a leading order, the small body's metric as if it were isolated. Then we have new perturbations that are functions of s tilde. Now we can develop a matching condition, which if you've learned any singular perturbation theory should look familiar. But if not, should be clear anyway. So what we do is we take our outer expansion, our original one up here, and we re-expand that in powers of this small distance s. So we're expanding it near the world line, which puts us in that buffer region. So now we have a double expansion. We have an expansion in powers of epsilon, which was already present up here. And now we have an expansion in powers of s. And these coefficients are now independent of epsilon and s. Now, initially, we don't know if we include negative powers of s. We think obviously we should have some negative powers because we expect the field of the body getting stronger and stronger as s gets smaller, as we get closer to the body. The key thing is we have this double expansion in these two small quantities, epsilon and s. Now what we can do is we can take our inner expansion and re-expand for small epsilon. And when we do that, but we expand for small epsilon at fixed s, not at fixed s tilde. When we do that, we get another double expansion. So we have functions like this that are functions of s over epsilon, and we're expanding in powers of epsilon. That means we're going to get combinations of epsilon over s to some power. And we're taking s now to be large compared to epsilon. So distance is large compared to the mass. That's what's happening when we're taking this series and expanding in powers of epsilon at fixed s. So we have two different double expansions. And basically, we're going to insist that the expansions commute. So if we expand first in powers of epsilon and then in powers of s, or if we expand basically first in powers of s and then powers of epsilon, we're going to get back to the same double expansion. So what that means is the coefficients here in these two double expansions have to match term by term. Now, because the series looks somewhat different, because here you have epsilon over s to the p, and here you just have s to the p, there's shifting in the indices. But all that matters is the basic idea that these two series have to agree order by order in epsilon and s. So there's a relationship between the coefficients. So you can think, well, okay, so you can think intuitively, yeah, both of these are accurate in the buffer region. It turns out you can construct functions that satisfy this matching condition where actually the double expansion is not accurate anywhere. It doesn't actually matter. But you can intuitively think of it as, yeah, we're re-expanding everything in this buffer region, and we have some accuracy there, so the two things should agree intuitively, yeah. So you can also, rather than imposing a matching condition like this, you can also impose certain smoothness conditions on the metric as a function of coordinates and epsilon. But this is the less conservative, no, more conservative. This is a much weaker assumption than smoothness conditions. Okay, so what happens here? So I mentioned that we have negative powers of s potentially, or we expect there to be negative powers of s when we re-expand in that buffer region. But now we assumed to begin with that our inner expansion is well behaved in some sense. We're assuming both of these expansions are well behaved, otherwise why are we even writing them down? So what do we mean by well behaved? Well, at fixed s tilde, we don't have any negative powers of epsilon. We don't diverge in the limit as epsilon goes to 0. If you just took a random region of space-time with no body inside it, you would mess things up by working in these scaled coordinates and then taking epsilon goes to 0. But if there's a body inside it, then the body's gravity should be supporting these functions of s over epsilon. Okay, so we're assuming that there's no negative powers of epsilon at fixed s tilde. Then what that means is we have a constraint on the most singular power of s in the outer expansion. Now, how do we see that? Well, if we take epsilon to the n over s to the n, so this is what we have in the outer expansion when we take h and re-expand for small s near the body, then rewrite that in terms of s tilde. And remember that we are not allowing any negative powers of epsilon at fixed s tilde. So we take epsilon to the n over s to the n from the outer expansion, rewrite it in terms of s tilde. And that introduces an epsilon to the n on the bottom, and the epsilon to the n's just cancel. So if I have something in my outer expansion that looks like epsilon to the n over s to the n, and then rewrite it in terms of things in the inner expansion, it actually becomes independent of epsilon. It's an epsilon to the 0 term. It's just 1 over s tilde to the n. Now, if I put s to the n plus 1 on the bottom, then I would have a negative power of epsilon. Because if I had s to the n plus 1 on the bottom, I'd have epsilon to the n plus 1 on the bottom, and then I have 1 over epsilon. So this is telling us that if our outer expansion matches an inner expansion, and if the two expansions are well behaved, then the most singular power of s you can have in the outer expansion is 1 over s to the n. You can't have 1 over s squared at epsilon to the 1. Okay, so say we take the nth order perturbation and expand for small s. So as I just explained, the most singular term can just be 1 over s to the n. You can't have s to the n plus 1 or anything. And then you have subleading terms that are smaller powers of 1 over s. So again, think of Coulomb potential, or just Newtonian potential, or even Schwarzschild potential. You have m over s, mass over s. And then all the higher order terms in powers of m come with higher powers of 1 over s. So in fact, this leading term here, if n equals 1, is just the Coulomb term, just the mass over s. And as you go higher order in perturbation theory, so as n goes up, you get higher powers of 1 over s. So this leading term, as I showed up here, rewritten in terms of s tilde, is independent of epsilon, meaning it has to match something that's in the background geometry in the inner expansion. So this leading term, is 1 over s tilde to the n, must be coming from the asymptotic expansion of the body's metric, because it's independent of epsilon as a function of s tilde. So if you take the body's metric and expand at large distance, as I said, you can read off the multipole moments of the space-time. It's mass, it's spin, it's quadrupole moment, etc. And what we're seeing here is that this leading term for small s in the outer expansion is then determined by the multipole moments of the isolated body that's being seen in the asymptotic form of its metric. So at first order, we get the mass of the small body. At second order, we're going to get the spin. Third order, we're going to get the quadrupole moment, etc. Okay, now this I derived without actually imposing Einstein equations. I was just considering the form of the two expansions. But now I want to substitute that expansion into the Einstein equations. So I have this Hn, and I'm going to expand it for small s, meaning I get 1 over s to the n plus 1 over s to the n minus 1, 1 over s to the n minus 2, etc. Substitute that into the Einstein equations. And I'm then going to solve order by order in epsilon and s. So I'm solving the Einstein equations outside the body for this perturbation h at small s. I'm also going to expand each of these coefficients. So this is the coefficient of epsilon to the n over s to the p. And expand each of those coefficients in spherical harmonics around the small body. Then what you find when you go through the algorithm is in the Lorentz gauge in particular, you're given a world line gamma representing the motion of the small body. Then the solution to the Einstein equations to all orders in epsilon and all orders in s is fully characterized by a discrete set of moments. So there's the body's multipole moments, which come in this form. We have 1 over s to the L plus 1. And then you have smooth solutions to the vacuum wave equation, which come in this form, s to the L. So these forms should be familiar just from standard electrostatics. you just look at the solutions to the Laplace equation, this is the form of the solutions. S to the L and 1 over S to the L plus 1. And you find that you can write down the solution to all orders in terms of the coefficients of something like this and the coefficients of something like this. Every other term is a linear or nonlinear combination of these terms. Now you further find that you get a very nice split, not a unique split, but a nice split between what we can call the self field of the small object and its regular field. What do I mean by that? Well, the multipole moments that come in here are basically the background space-time of the small body plus perturbations to that, deformations of that due to the external geometry. And so I can take all the stuff that's only determined by the multipole moments of the small body and interpret that as the self field of the body. It's kind of just moving along with the small body. Then I can take all these smooth, homogeneous vacuum solutions and define a different piece of the field, which we'll call HR. This is more like free radiation. This is just propagating independently of the body. You don't see the multipole moments of the body directly in this field. This is a solution to the vacuum equation, even if I extend it all the way down to this representative world line gamma. And HS, the self field, is basically determined locally, whereas HR, this regular field, is only determined once you impose some global boundary conditions. So first and second order, what do things look like? So at first order, we have a self field plus a regular field. The self field is the mass of the small body. So this is actually like the ADM mass of that inner background spacetime divided by distance from the body. So every term in the small s expansion of this is just exactly proportional to the mass of the small body. And it's known analytically, locally. Then you get this term HR1, which is, if you're doing just a local analysis with no global boundary conditions, HR1 is just a homogeneous solution, and it's just a list of unknown functions of time, effectively. The self field, if you extend it down to s equals 0, is singular there. This HR1, when extended down to s equals 0, is not just smooth, but it's a homogeneous solution at s equals 0. It's a vacuum solution at s equals 0. So that's first order. At second order, you do the same analysis. And what happens is you just get higher multipole moments of the small body and more singular powers of s. So again, we're going to have a self field and a regular field. The self field now starts at 1 over s squared, so it's more singular at s equals 0. You have some terms that are just mass squared, but then you also get the spin of the small body coming in. So there was the question earlier of where do the finite size effects come into this? Here's one place. The spin comes in at second order. Then you have subleading terms that are 1 over s, and in these terms, you get something like a correction to the monopole, not really a physical one. And you get things that are like mass times the first order regular field, and then subleading terms. So now the self field is determined by this correction to the monopole, spin dipole, and these terms are like mass times first order regular field. So nonlinear terms. Yeah.
Multiples
we already extended our time. So we could do that at the end, let us not ask questions. And so please try to
Okay.
finish.
Do I have a good conclusion point here? No, I don't. It's going to be multiple slides. This would be the natural conclusion point. Do I have time for 2 slides? No? Okay. We're going to pick that up tomorrow then. So this is the local form. Tomorrow we're going to talk about how we take this local form. And first off, I'm also going to talk about how the body is moving. That's the other thing that comes from the local analysis. And then I'll talk about how to take this local form and feed it into some way of solving the Einstein equations in the external spacetime. Okay, so get that tomorrow.